This is a video from section 5.5. The directions say to evaluate the indefinite integral. So my goal in this video is to give you a lot of looks at a lot of different examples. All right. So we're going to start here with example 1. Suppose I had the integral of, we're going to do this one, sine of x divided by 1 plus cosine squared x dx. So this is a U-substitution problem. So I'm going to let u be cosine of x. du is negative sine x dx. So when you find a u and choose it, you want to make sure the derivative is present somewhere in the integral. So like, for example, if I let u, see the problem with letting u be sine of x, okay, you can try that, but du is cosine of x dx. So if I write this down, I see the dx, but there's no cosine of x. Yes, there's 1 plus cosine squared x in the denominator, but you need a cosine x as a standalone. And that's why when letting u be sine x doesn't work. And that's why I chose u to be cosine x. Because notice how sine of x is a standalone. Right there. It's kind of the idea. I hope that made sense what I was trying to say. And so sine of x dx, so if I solve for that, I get negative 1 du. So I'm going to replace that. And so I'm going to get negative 1 divided by 1 plus u squared du. And so this is negative arctangent of u plus c. But remember that u is cosine of x, so you always have to put your answer back in terms of x. So this is negative arctangent of cosine of x plus c. And that's how you do example 1. Let's take a look at example 2. Suppose I had the integral of cosine of natural log of t divided by t dt. So I happen to know that the derivative of the natural log of t is 1 over t, right? And so it might help you to look at the problem this way. So I have cosine of natural log of t times 1 over t dt. So I would look at it this way. And the natural log of t is an inside function, and so that makes a great choice for you. Okay? And then du is 1 over t dt. So you're taking the differential of u. And then that's the notation we use for when we integrate. And then here I'm going to take the integral of cosine of u. Okay, so I replace natural log of t with u, and then 1 over t dt becomes my du. And remember, what's the function whose derivative is cosine of u? And so that just so happens to be sine of u. So the answer is sine of u plus c, but remember, we have to put it back in terms of t. So one step further, we're going to get sine of natural log of t plus c. And that right there is the answer to the second example. Let's take a look at a third example. Suppose I had the integral of x over 1 plus x to the 4th dx. This one's a little tricky because I'm thinking I want my du to end up with some scalar multiple of x dx, okay? And so I'm going to write this as x over 1 plus x squared dx. Because that makes a good candidate for u. So in other words, I'm going to let u be x squared. du is 2x dx, right? And then remember though, you want to solve for x dx. So x dx is 1/2 du. And so what I'm going to do is I'm going to have the integral of 1 over 1 plus u squared, right? So I replace x squared with u. And then dx, x dx, is going to be 1/2 du. So I'm going to pull that 1/2 on the outside, and I'm going to integrate 1 over 1 plus u squared du. And so the answer here is 1/2 arctangent of u plus c. But if you recall, u is x squared. So this is 1/2 arctangent of x squared plus c. And that is example 3. So let's take a look at example 4. Suppose I had the following. We're going to talk about this one. Suppose I had x squared times the square root of x plus 2 dx. Here's what I'm going to do. I'm going to let u, this is a good candidate for an inside function. So I'm going to let u be x plus 2. So are we in agreement that du and dx are the same? Okay. So this is what we're going to do. We're going to have the integral of, now dx gets replaced with du. X plus 2 is u, so I'm going to have the square root of u. But remember, x is equal to u minus 2, right? So I'm going to replace the x with u minus 2, so I'm going to take u minus 2 and then square it. So this is the integral of u squared minus 4u plus 4 times square root of u du. Now I have to distribute the square root of u in. That's still a more manageable integral than the original. All right? So let's rewrite this. So we have square root of u times u squared minus 4u plus 4 du. And I'm going to distribute the square root of u in. So I get u to the, now, square root of u, remember, is u to the 1/2. And 1/2 plus 2 is 5/2. So we get u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2 du. Okay? Now, when we take the antiderivative, we're going to get u to the 7/2, right? If we add 1 to 5/2, we get 7/2. But when you divide by 7/2, that's the same thing as multiplying by 2/7. Okay? Minus 4 times, now here we have u to the 5/2, right? So remember that 3/2 plus 1 is 5/2. And then we're going to multiply by 2/5. Plus 4 times, now 1/2 plus 1 is u to the 3/2, right? And we're going to multiply by 2/3. And then don't forget our constant of integration. You're looking for a family of functions. And so here, remember that u is, in this problem, was x plus 2. Yep. So I'm going to take x 2/7 times x plus 2 to the 7/2 minus 8 over 5 times x plus 2 to the 5 halves plus 8 thirds times x plus 2 to the 3 halves plus c. And that was example 4. So let's do a few more examples for this video. And so in this problem, we're going to evaluate the definite integral. And when I talk about a definite integral, I'm talking about an integral with limits on them. Okay? Now, let's do a problem here. I think this is a good place to start. So let's say we have the integral from 0 to 1 of 3x minus 1 to the 50th dx. So on its face, that looks horrible, okay? But I want to teach you how to do this. The inside function here is 3x minus 1. So I'm going to call that u. Du is 3 dx. Now I'm going to solve for dx, and I'm going to get 1/3 du. But one thing you have to remember is that the limits are in terms of x, and you want limits in terms of u. And so this is what we have so far. Now, I'm going to replace u with 3x. I'm going to replace 3x minus 1 with u. So we get u to the 50th times 1/3 du. Because I replaced dx with 1/3 du. Now, when x is 0, can we agree that u is -1? So that's what goes here. When x is 1, u is 2. That goes up here. Now those limits are in terms of u, and we're in business. And so I'm going to pull the 1/3 out in front, and I'm going to integrate from -1 to 2 of u to the 50th du. And so over here, I get 1/3 times 1 over 51 u to the 51. That's a manageable integral from -1 up to 2. Now, 3 times 51 is 153. So you get 153 times. I'm going to pop the upper limit in. So in other words, I'm going to replace u with 2. So I'm going to get 2 to the 51 minus -1 to the 51. So this is 1 over 153 times 2 to the 51 plus 1. I cannot imagine your instructor will want you to carry out what 2 to the 51 is. So that would be a very acceptable answer. And that's how you do, we'll call this example 5. Okay? Let's talk about example 6. Well, suppose I had the integral from 0 to 1 of e to the x over 1 plus e to the 2x dx. And what you need to think about is rewriting this as e to the x over 1 plus e to the x to the second power. So that's what e to the 2x is in disguise. And that gives us a nice u-sub. So I'm going to let u equal e to the x. So in other words, I'm going to let u be this inside function right here. So du is e to the x dx. And so we get the integral of 1 over 1 plus u squared. But notice how e to the x dx became my du. But we have to figure out what the lower and upper limit are in terms of u. So I'm going to plug x equals 0 and x equal 1 into here, what I have boxed. So when x is 0, u is e to the 0, which is 1. And when x is 1, u is equal to e to the first, which is e. And so I'm going to go from 1 to e. And so this is arctangent of u evaluated from 1 up to e. And the nice thing is, once you put everything in terms of u's, you don't have to transfer back in terms of x's. It's only when you do indefinite integrals that you have to put back, not definite integrals, because with definite integrals, you're looking for a number. And so over here, this is equal to arctangent of e minus arctangent of 1, which is arctangent of e minus pi over 4. Your instructor will want you to probably know that arctangent of 1 is pi over 4. So this would be a very complete answer. And that's example 6. Let's hit another one, example 7. Suppose I gave you this one. 0 to pi over 2 of cosine x times sine of x dx. Don't forget that dx. And so the inside function to me looks like sine of x. So I'm going to let u be sine of x. Du is cosine of x dx. Now, again, you have to transform those limits in terms of u. So when x is 0, u is sine of 0, which is 0. And when x is pi over 2, u is sine of pi over 2, which is 1. So it's very important to get those limits in terms of u. And so I'm going to go from 0 to 1. So u equals 0 to u equal 1 of sine of u du. And so this is negative cosine u, right? That's the function whose derivative is sine of u, evaluated from 0 to 1. So you get negative cosine of 1 plus cosine of 0. But cosine of 0 is 1, and so the answer, let's come over here. The answer is 1 minus cosine of 1. And I would say let's do one more. We'll round it to 8. So on this, I'm going to do this one. Suppose I had the integral of okay, so we're going to go 0 to 2 of x minus 1 e. We'll do this one. X minus 1 e to the x minus 1 squared dx. This one's not bad. And so the inside function looks like it's this. So we're going to let u be x minus 1 squared. du is 2 times x minus 1 dx. So this is a chain rule, power rule, kind of a combination, because remember that the derivative of x is 1. And so x minus 1 dx is 1/2 du. Okay, now what you don't want to forget is to transform those x limits in terms of u. So when x is 0, u ends up being negative 1 squared, which is 1. And when x is 2, u is 1 squared, which is 1. This is a good problem. Okay, I like it. Because now watch what happens. So I'm going to take the integral of e to the u times 1/2 du. And I claim none of that matters because the limits are from 1 to 1. The minute the upper limit and the lower limit are the same, the answer is 0. And you're done immediately. Okay, that concludes this video for section 5.5, and it's on U-substitution, where we worked out 8 examples. Thank you.